All right, welcome back, Physics 2. Isn't this fun how technology has made our lives better, and yet at the same time I cannot record much more than 45 minutes at a time. Okay, so where we left off last time, we were just dying to find out the width. And so we have a path difference between the two slits being n over 2 times lambda. So we have n over 2 lambda plus 1/2 lambda. Oh, I'm now been thrown off. So if there is a minimum, or so a minimum, the path needs to be an additional lambda over 2. So we would have n over 2 lambda plus 1/2 lambda. Okay, so now we're going to be moving along, and let's look at the next pair of slits. So not dissimilar to what we did with the bubble. So this would be number 2 and n over 2 plus 1. These also have a path difference of lambda over 2. And eventually you can pair up all the slits so they contribute 0 intensity. So this is a game we've played before. So in this case, theta plus delta theta is equal to 0. So d sine theta plus delta theta is equal to lambda plus a little epsilon, and epsilon is a small fraction of lambda. And the path difference between the first and the n over 2 is n over 2 times lambda plus epsilon is equal to n over 2 lambda plus 1 over 2 lambda, and therefore little epsilon is equal to lambda over n, where n is the number of slits and lambda is the wavelengths of light. All right, so moving on. Using trig identities, for two adjacent slits, d sine theta plus lambda theta is equal to lambda plus epsilon is equal to lambda plus lambda over n, and d sine theta cosine delta theta plus d cosine theta sine delta theta is equal to lambda plus lambda over n, and delta theta is a small angle. So cosine delta theta is approximately 1, sine delta theta is approximately delta theta, and d sine theta plus d cosine theta delta theta is approximately lambda plus lambda over n. And if you recall, d sine theta is equal to lambda, so d cosine theta delta lambda, or sorry, delta theta is approximately lambda over n. And delta theta is approximately lambda over n d cosine theta. And the total width of the diffraction grating W is n times the width of one slit. So W is equal to ND, and delta theta is equal to lambda over W, which is the angular resolution equation we put at the very beginning. All right, so now you know where it comes from. So now we can talk about telescopes. So telescope resolution and diffraction. So what we see from telescope images is the light that has hit a series of photographic plates. This is try that again. This image is impacted by diffraction. And so this will spread the light out and approximate half angle delta theta is approximately lambda over W. This can sometimes cause the image of two stars to broaden to the point where we can't see two stars, just one blob. So when you're designing your telescopes, it's not just about magnification, it's also more importantly about angular resolution. So you can magnify all you want, but if you don't have the angular resolution, two different stars could end up looking like this. And then you can't tell the difference between the two of them. And so to fix that, you would need to resolve the image. And so that resolution power of a telescope is limited by the diffraction put in it. That's why we have telescopes that look at different wavelengths of light. So they're all fine-tuned to have resolution within a particular area. It's very expensive to make something that could be resolved in all areas, so you just have lots of instruments looking at different aspects, and you can put these images together. That's why many astronomers are excellent programmers. Okay, so the wider the lens, the sharper the image. Big lenses are very expensive though, so you're always balancing. Bigger W, smaller theta, and the shorter the lambda, the sharper the image. And in this case, you would have a smaller lambda, smaller delta theta. And so for observing stars, if phi, the angle between the stars, is greater than 2 delta theta for a particular telescope, the image is resolvable. And if it's not the case, you can't resolve it any further. There's no zoom in and resolve. You are limited by your equipment. We are always limited by our equipment and our grants. So, for example, green laser light, 520 nanometers, goes through a single slit whose width is 0.007 millimeters. What is the width of the image on a screen 7 meters from the slit? So, the angular width of a maximum, so delta theta equals lambda over W. This is actually the half width. The angular width is 2 delta theta is equal to lambda over W. It's the angular width. And so delta theta is equal to 2 times 520 times 10 to the minus 9 meters over 0.007 times 10 to the minus 3 meters. And so delta theta, or the angular width, is equal to 0.149 radians, because yes, this is in radians. Okay. So the width on the screen is at the arc length distance (7 meters) from the slit. And arc length is S is equal to R theta is equal to 7 meters times 0.49 radians is equal to 1.04 meters, and therefore the maximum on the screen is 1.04 meters wide. And there you have it. All right, well, that wraps up Physics 2. It's been a very interesting semester. I have appreciated how smooth all of you have made this online transition. It wasn't what I wanted. It wasn't what you wanted, but I think we've really made the best of it. Hopefully you've learned some cool things. I'm very sad I did not get to teach Gauss's laws of electromagnetism in person. It's one of my favorite things that I do all semester long. So I hope that you still enjoyed them, that you still got a lot out of them, and that if you enjoyed these last sections all about light. Anyways, please do not hesitate to reach out for questions, and I wish you all the best.